Euler's method is a numerical approximation for a differential equation. It's really just repeated tangent lines. So if we have dy dx, that's equal to xy with the initial condition, f of 1 is equal to 3, and we want to use 2 steps of equal step size to find an approximation for f of 3. So we always do 2 steps on the AP test. Start with writing your x's, so that would be your initial condition would be x0, y0, so 1, 3. Then you have x1, x2, because those are going to be 2 steps, and then y1 and y2. So we wanted to approximate f of 3, so that's going to be our last x. They're all equal step sizes, so the middle one would have to be 2. H is what you add from getting to one place to the next. So of course, 1x to the next x, and it's always equal for us. H could also be negative. So if we started with f of 3 and we wanted f of 1, then your step size would be negative. But our step size is positive 1. So the formula is yn plus 1 is going to equal yn plus h times the derivative. And you're always using your previous point. So if I'm going to find y1, I'm going to use x0 and y0. For our formula, then it'd be y1 is equal to y0 plus h f prime of x0, y0. So y0 is 3. Our step size was h. The f prime is our differential equation. So for us, we're just multiplying x and y. So 3 times 1 is 3. So our next approximation is going to be 6. So that goes right here. So now on the next step, we're going to use this one and this one to find our next y. So y2 is going to be y1 plus h f prime of x1, y1. y1 is 6. H is 1. And this time we're going to plug in 2 and 6 into our differential equation, which would give us 12. So our approximation is 18. So f of 3 is approximately equal to 18 using 2 steps of Euler's. Now, we could also talk about if this is an over or under approximation, because what Euler's is you're approximating using repeated tangent lines. So if I was trying to approximate this curve using just one tangent line, and I started here and I wanted to find the value over here, you'd follow the slope for a certain amount of time. If you're doing Euler's method, you take several different steps. So here would be 2 steps. I'd follow it for this amount of time, and then we'd readjust our slope. So it should be a better approximation. But it's going to have this same error type as a tangent line. So if it's concave up, it'll be a under approximation. If it's concave down, it'll be a over approximation. So we can look at the second derivative to determine the concavity at that point. Now, of course, we'd have to make sure that it didn't change concavity throughout the whole Euler's method, because each time that approximation goes off that new point. But since we're just going to assume this is all concavity in one direction, which we shouldn't do, but so the derivative of x is 1, and then xy prime, and we want to find the second derivative at 1, 3, which was our initial condition. So let's see, y was 3, x was 1, and we already calculated y prime to be 3 for the first step. So this is going to be 6. So since that's concave up, we know that this is going to be an under approximation. Another thing they could do with, to do a little bit different, to add something to Euler's method, they can say, hey, go back to this original problem, and I want you to find the degree 2 Taylor polynomial. So we're going to find the P2 Taylor polynomial centered at 1, because that's where our information came from. So remember, we're going to have f of 1, f prime at 1, x minus 1, f double prime at 1, x minus 1 squared, all over 2. So f of 1 was 3, f prime of 1 was 3, and then the second derivative was 6. So 6 divided by 2 is 3. So this would be a P2 Taylor polynomial that would solve or give an approximation to that differential equation. We could actually solve this differential equation also because it happens to be separable. So here we have dy dx, which is equal to xy. F of 1 is equal to 3. So separate this, we'd get 1 over y dy is equal to x dx. Integrate both sides. So natural log of y is equal to 1/2 x squared plus c. Exponentiate both sides. So you have y is going to be equal to c e to the 1/2 x squared. And then, of course, y is 3 when x is 1. So we know c has got to be 3e to the negative 1/2. And then, of course, we can plug in and find out exactly what it would be at x equals 3. We could have used our Taylor polynomial to do the same thing. So if I wanted to do P2 at 3, you would just plug all those things in. So 3 plus 3 times 2 plus 3 times 2 squared. And let's see what we get here. So 3 plus 6 plus 12, so 21. So I don't know how good or bad that is, and then we can find the real value also. If you want to make Eulers more exact, you would take more steps. If you want to make a Taylor polynomial more exact, you do more degrees. So you would take more derivatives and have more terms.